Now we're going to look at section 4.3, which is all about eigenvectors and eigenvalues. This caps off our study of linear algebra and matrix theory back a while in LA1, and it caps it off with the eigenvalues or roots that determine the behavior of your system. We'll find out these eigenvalues are really just the characteristic roots we've been finding using the characteristic equation method, only written in a slightly different form, in matrix form. So let's talk about the eigenvalue problem. The definition of an eigenvalue and an eigenvector are intertwined. Given a matrix A, our coefficient matrix, our goal is to find eigenvectors V that are not the zero vectors and eigenvalues lambda, which are scalars, such that you can reduce matrix multiplication by that V into scalar multiplication. What this says is that we are looking for particularly well-aligned vectors, eigenvectors, whose transformation in multiplying by A moves them along themselves, grows the vector in the same direction or opposite direction, parallel to the original input vector. So if you think of that as your input vector, if you find the particular structured eigenvector structure for this matrix, then the output of this transformation, A times V, will simply be a multiple of that input piece. Let's look at examples of taking matrices and just testing them with certain structure, certain vectors, to see if we can find, just by inspection, some eigenvectors. Okay, so for our example, we have -3, -1, 0, -5. Now, one thing we will notice about this, it has a particular pattern to it. It is an upper triangular matrix, and that is actually quite important. We'll see some of these patterns pop up a little bit. But first, we want to test it against some vector. So let's just try a few. Multiplied by 1, 1. I get a -3 minus 1, so that's -4, and a 0 minus 5. Just to remind you how matrix multiplication works, that resolves to a -4 and a -5. Now this is really close to a multiple of 1, 1, but it's not. But being really close means that we're in the ballpark of the structure eigenvector for this matrix. So let's see. What if instead of a 1, 1, we do a 1, 0? Now this is taking advantage of the upper triangular nature of this matrix. I get a -3 plus 0, and then a 0 plus 0, which is -3, 0. Is that a multiple of the input? Yes. So now I know that 1, 0 is an eigenvector, and it's associated with lambda equals -3. So we have the eigenvector, the eigenvalue-eigenvector pair of -3 and 1, 0. Okay, now it might be hard to find another combination, but let me just look at this -5. You notice back when we had 1, 1, we were really close. And we shifted it once by dropping the 1 here, and we were able to land right on that -3 multiplier. But let's instead of decreasing the 1, let's try increasing the 1 a little bit. 1, 2. Okay? So I'm multiplying it through. I have a -3, and then I subtract 2 from that. And on the bottom, I have 0 and a -10. So that gives me a -5 and a -10. And I check, is that a multiple of my 1, 2? Yes. With eigenvalue -5. So I have the eigenpair -5 and 1, 2. So I found 2 eigenpairs. And just like characteristic equation, the number of eigenpairs is related to the size of the matrix, just like the number of roots is related to the order of the differential equation. Because it's a 2 by 2 matrix, we're expecting 2 eigenpairs, or at least 2 linearly independent eigenpairs. One other thing to notice is that I mentioned earlier that I'm taking advantage of the upper triangular structure of the matrix when I chose 1, 0. And that's because the 1, 0 only hits this exposed diagonal element and doesn't hit any other term. And so I basically pick off that -3. And you'll notice that -3 is an eigenvalue, and so is -5. When you have an upper triangular or lower triangular, really any triangular matrix, the eigenvalues are staring you in the face. They're right down the main diagonal. You just pull them right off. The -5 was a little bit harder to get to. Notice that we had to be a little bit more creative, but it worked out. So that is one way to kind of guess at eigenvectors and eigenvalues just by looking at patterns in the matrix. Now, let's look at systematically how we can find and compute eigenvalues and eigenvectors. So we solved the eigenvalue problem in 2 steps. First step, we find all eigenvalues, lambda, such that, or I should say, satisfying the determinant of A minus lambda I set equal to 0. And we call this thing the characteristic equation for matrices. And sometimes we'll relate it very directly to our characteristic equation for finding roots of differential equations, and we'll just use an R to represent the eigenvalue lambda. Because really it's the same thing. The characteristic roots in solving constant coefficient homogeneous differential equations yield the same results as the eigenvalues of a matrix. They're just written in 2 different ways. Secondly, for each lambda, we find the associated eigenspace by solving A minus lambda I augmented with 0 and choose linearly independent representatives V. Now, there's a lot of theory that goes behind this procedure of finding the eigenvalues and the eigenvectors, but I wanted to at least tell you the process first so we can see it, what's happening here, and then go through some examples of using it, and then see some of the theory about why exactly it works. So, let's start with our previous example, -3, -1, 0, -5. If we take the determinant of A minus lambda I, and I'm going to write it in terms of R, A minus Ri, what I get is a -3 minus R, a -1, 0, and a -5 minus R. And I want to set that determinant equal to 0. Okay? Choose this column with the 0, and I have my -3 minus R multiplied by what's left. Well, sorry, multiply down, subtract 0. There you go. -5 minus R equal to 0. And then I solve for the roots by expanding and factoring, but it's already factored. So I can see that R equals -3 and -5. Again, what I noticed before, that pattern in terms of the main diagonal for a triangular system, is true. That is the eigenvalue. Those are the roots that make the determinant of A minus Ri equal to 0. Now, I want to look at each one of those and find the associated eigenvectors. So for R equals a -3, I'm looking at A plus 3i augmented with 0 equals, I'm adding 3 to each diagonal element, so I get 0, 0, -1, and -2, 0, 0. And I want to solve for the eigenspace, or the relationship between the components here. So I have no pivot here, which means I move over to my -1 as my pivot, and I clear below. It's pretty obvious. I mean, we know what we want to do. We want to use -1. We take R2, we subtract 2 copies of that R1. It's just going to clear it out. You can see it's a multiple on the bottom, and we'll end up with 0. Oh, might as well gate that. +1, 0, 0, 0, 0. Okay. So we cleaned it up to a point where we have it in a reduced row echelon form, or at least in a reduced system that we can use to solve it. And what this first equation says is that V1 equals 0. The second equation says nothing, but we know, V2 is equal to 0. V2 is equal to 0. The second equation says nothing, but we know that there's a free variable in V1, so V1 is free. And if we write that together, we get V1, V2 equals V1, 0. And if we factor out of V1, our free variable, we get 1, 0. So we know that -3 is paired with 1, 0. Like we had before. Now, what's interesting is that we now know that it's not the only vector, eigenvector. Every multiple of 1, 0, like 2, 0, 3, 0, pi 0, every multiple, every non-zero multiple of this eigenvector is another eigenvector. So that's why I say when we solve the equation, we're solving for the eigenspace, we're solving for all the possible eigenvector solutions, and then we choose a simple form of it, a representative, a linearly independent piece. So you'll notice that when we solve for R, the eigenvalues, we get distinct values. We know we just solve the quadratic or whatever form it is. We find the roots. And the eigenvector, we actually solve for all possible eigenvectors, and then we choose one, or possibly two, depending on if there's more than one free variable. We choose one per free variable. That's what we do. If there's only one free variable, we only choose one. If there's two free variables, we choose two, one for each one. And now let's do the same process for r equals -5. I remember before that we had the vector 1, 2. So let's see if we can get that, or at least get a form that's similar. Subtract the root, or the eigenvalue, so we are adding 5. Get 2, -1, 0, 0. Well, this is convenient. It already cleared the bottom row out for us. So now we just need to row reduce in a sense. And so let's take row 1, divide by 2 to get that into a 1, just to make it row reduced. 1, -1/2, 0, 0, 0, 0. And then we can read off that first row. That says V1 equals, move that -1/2 over to the right, V2 over 2. And then V2 has no pivot, so it's free, equals V2. And if we write that as a system, our V is equal to V2, the free variable, multiplying a 1/2 vector and a 1. So this is the eigenvector that came out most clearly, but you'll notice that if we scale each component by 2, if we choose V2 to be 2 in this case, we can get back to our 1, 2 vector for -5 that we found before. Or we could just keep the 1/2 there. I like to choose a multiple that makes it as simple for me to work with as possible. So I like to make that first term, or I like to make all terms integers if possible, and try to make that first term positive. It just helps me in terms of using the vectors for the solution later. So there we go. We have an example where we consistently went through the process and found the eigenvalues and eigenvectors. We got the same pair, or at least we're able to show that the one we found before are in the same family of eigenpairs as the examples where we guessed at it and found it. So now I'm going to erase this out and talk about the theory of why this procedure works, where this determinant comes from, and how we're able to solve for the eigenvalues by making the determinant of a minus lambda times I instead of equal to 0. One thing to think about is whenever we've seen determinant equal to 0, that means there's no unique solution. Right? Determinant not equal to 0 is what we needed when we were working with Cramer's rule and finding that unique solution. So this is the opposite of what we usually deal with. And then solving with a matrix augmented with 0 means that our right-hand side is 0. We're solving for the homogeneous solution. Or, if you remember terminology here, we're actually solving for the null space. And that's what this thing is. The eigenspace is the null space of this modified matrix we already took the determinant of. The null space represents all possible solutions to that matrix times a vector equal to 0. So those are the key ideas we're going to dig through.